Hello, everyone, and thank you for joining us for today's Würth Electronic webinar, and actually one of the last webinars for 2022. We only have 3 left, but don't worry, we will be returning in 2023. Today's webinar is Efficient Filter Connection in the Layout, of course, partnered with our friends over at DigiKey Electronics, the exclusive sponsor of all Würth Electronic webinars. And today's presenter is our very own Robert Schillinger. He's a field application engineer at Würth Electronic. Of course, I'm your host, Amelia Thompson. And if you have any questions during today's webinar, simply ask them in that questions box, and we will answer them at the end. Now, if you need to go into detail about a project, or maybe you think of a question a little bit later, simply email our team. It's webinarteam@we-online.com. Again, webinarteam@we-online.com. That email is also where you will receive the video on demand and the presented slides. Because you registered for today's event, you will automatically receive those within the next week or so, depending on when we can get that video edited and sent out. Simply look for that email link in your email. Don't miss out on our next webinar. It's coming up next week, the second to last webinar with Frank Puhani. He is returning to present DC link capacitors, specifications, and applications. You can register online at www.we-online.com/webinars. Now I'm going to hand it over. Let's begin today's Würth Electronic webinar with Robert Schillinger, Efficient Filter Connection in the Layout, partnered with DigiKey Electronics.
Okay. Yeah, thanks, Amelia, and welcome to our presentation today. I will start and hope you can see the start slide. My name is Robert. Amelia is talking about me. I am a field application engineer at Würth Electronics since 2014 in the company. And today I will show you some things about filters onto PCBs and how it works and interoperate with the component parasitics. I will show you something about the ideal and the real world where the components are in simulation, for example. I will show you especially the parasitics of PCB, especially the wires and how it interacts if you use more than one of wire, and what happens with the filter characteristics. Second point of the presentation is some simulations about real filters with bias effects of capacitors and all the bias effects of inductors, or in this case of ferrites, and how it interacts with the result. That's the program today. Let us start. I will give you a short overview over the measurement equipment we are using for this presentation. We create a small PCB, you can see on the left side, and on the right side, the corresponding layer stack for it. The important thing is the top layer and the first inner layer, which is the reference ground of the systems to reach the 50 ohm impedance for matching with the measurement equipment. All other layers, the second internal and the bottom layer, are completely the same potential like the first inner layer and is ground. Yeah, we have on the board the possibility to compensate the measurement equipment and to calibrate directly to the connectors on the board. And then we compare some different schematics, like a pi filter in several constellations, like you can see in the middle. I show you with the laser pointer here. With this constellation in parallel of the filter components or in a typical pi structure, also some smaller components in 0603, and how it looks like for the attenuation of the complete filter and what happens. Yeah, let us start with the parasitics of the important and used components. On the left side, you can see the capacitor. We have the ESL of a capacitor caused by the contacts or the input lines. The typical ESR, you know from some diagrams, the real C value and the parallel resistor, the leakage, which is responsible for the leakage current of a capacitor. That's the most important parasitics of a capacitor you should use in a simulation to get a good result. And the same you can see on the right side for an inductor, and in this case, especially for a ferrite. You have here also an ESR, which comes from the copper winding or the silver structure of a ferrite from the RDC, and you have the real inductance and also the parasitic interwinding capacitance between the single windings in the component, and also the parallel resistance of this component. And if you put all these parameters and parasitics into the simulation, you come here on the left side of the capacitor from the black line, which is the ideal capacitor without any parasitics, what is not real good for simulation, because you can see with increasing frequency you have no bad side effects, and for this you must use the parasitics and get the blue curve, and then you get a typical resonance point, and then the capacitance value, which you can see here, is switching to inductance value. The same we get for the ferrite. Also, the black line is the ideal ferrite simulation, but this is also not the truth. You must change to the blue line, and also here you can see you get an increasing value of the impedance up to a maximum. That's the resonance frequency, and then it goes to the capacitive part of the component, and the impedance drops down with increasing frequency. Let us have a look onto the PCB itself. We have tracks and wires on the PCB. I will start with the track with a microstrip in this case. We have the track on top, and on the bottom side the reference return path, in most cases the ground. And I put here the table with some different widths and thicknesses of the PCB and the resulting in inductance in nanohenry per millimeter, caused by an epsilon R of 4.6. You get for a 4 millimeter line around 0.7 nanohenry per millimeter. If you decrease the distance to the return path to 0.288, it's the same like we used in the demo PCB or in the measurement PCB, then you can decrease the inductance value down to 0.35 nanohenry per millimeter. That's the fact. you can play with the width and with the thickness, and you get different inductances on the PCB. The same you have with wires on a board. In a simple case, you put from top to the ground on the bottom side on a 1.6 millimeter PCB. And maybe you can connect the filter capacitor directly to ground with such a construction. And here I give you an example of a 0.3 millimeter end diameter wire with 25 microplating. Then you have an inductance around 1.3 nanohenry, for example. If you go down to the 0.3 millimeter around, you shrink it down to 0.14 nanohenry. And that's important for a good working filter structure. I will show you in the next slides. A little bit different to the single construction is a wire on a multilayer, for example. And if you have, for example, 4 layers with a VCC and ground system, you get here in this point, because of the area around the wire, an additional capacitance of around 0.6 picofarad, which is an additional parasitics in the system. Now let us have a look onto the first pi filter with 08, 05 component size. And on the right side, you can see the LT Spice schematic, which I used for the simulation I show you in the next slide. And now we will see what happens with one wire and the construction here. It's a typical value. The simulation runs without layout and placement influence, and for this you get a very wideband attenuation and very high attenuation. That's the ideal thing you have in the simulation. If you reconstruct the filter to a nearly bad system, you put it close together and in parallel, then you get a lot of parasitics. For example, you get the inductance for this line, the line to the wire, and although in parallel here. You get additional capacitive coupling between the lines, the components, and the components here. And you get also an mutual inductance from the L5 to the other components, to the C9, the C10, and also to the copper lines here. If we put this parasitics into the LT Spice simulation, we have here the L5. It's only simulated as track, not as a component itself, with 1.4 nanohenry. The track to the capacitors with 0.45 nano, and the track to the via and the via itself with the track with 0.9 and the via with 0.14 nano. And if you simulate this, the gray one is the first simulation without any parasitics, and the yellow one is the result if you have an suboptimal placement and also a lot of parasitics on the board. And you see the attenuation will shrink immediately and in a very high value. The same we are measured on the board. I printed here all the measurements, and in comparison with the simulation, we get, I think, I would say, a really good and close result to the simulation. here behind, we use only the vias and insertion loss effects, and only the MLCCs are used, not the inductance and not the ferrite. We remove the ferrite from the measurement system and put in only an copper line. Back to the good board realization. The black one is the formerly yellow one, and if we go back to an the better realization, then we get the green one. In attenuation, we don't reach so much more, but in the frequency range, we see a shift to lower frequencies, and that's caused by the parasitics and the coupling effects of the components. That we also measured on the board and put it into the graphics here for the good layout. And in the next step, we reduce the size of the components to see how much is the influence of a smaller component or component composition. And this results in nearly the same things. It's not so much in between 0805 to 0603. The really important thing is the step from one wire to more than one, in this case to 3 wires, and in this case also in a special combination or placement of the wires. We try to find the maximum distance from each other in this way, together with a short connection to the pad itself. That's the point in this trial, to do this in this way, and we get such result. You can see in comparison to the violet one, we get more performance, a little bit higher in frequency. That's the big difference for only change from 1 wire to 3 wires. The same we can see in the simulation. We have the black one, the ideal one, which we are starting, the violet one, which is with 1 wire simulated, and the blue one with 3 wires. And we can place us in the middle of both. And this is really realistic. You have some possibilities if you are using 3 vias on a board. You can use it in this way with a maximum distance, and with the maximum distance you reduce the mutual inductance for or in between the wires. If you put it in this way, you have here nearly the same distance, but you get here a very long line, which additional inductance, and that's not so nice for this connection and for this connection. And in some, you have more inductance if you use the left one here. And the same you get here. If you put the wires close together, then the mutual inductance is increasing. The coupling will get a little bit higher. And for this, that the current is flowing in the same direction in each wire, you get the proximity effect as a result. And for this, the inductance is not decreased so much as we would like to have in comparison to this construction. That is also possible to simulate by a simulation tool, MCOS, and we have here the good construction with the wires far away from another. This is the green line here. The second one, the wires positioned in the row, is the with close together wires. That's the red one line, and the third one with the shifted to 0.5 millimeter distance. Then you get the blue one, and from the red one to the green one at around 200 megahertz, you have an attenuation of around 4 dB, which you can reach only by construction on the board. That's the influence of the positioning of wires for filters. We have a second influence of or to the filter from capacitor side and also from the ferrite side. And also here I will show you the effects at the capacitors. The black one is a typical simulation without any DC bias or voltage bias on the component. And if you use a biased model for a capacitor, you get the blue line. And you can see you have also a shift of the resonance frequency because the capacitance drops down, and for this the resonance frequency is shifting up. And if you have a look, for example, at 1 megahertz, you are increasing in impedance, and that's not so nice for a filter. The same effect happens, or nearly or a similar effect, that's the best word for it, you get for the ferrite, but here you have it not from the voltage side, you get it from the current which is flowing through the ferrite. But in principle, the same effect. The black one is without current. It's a measurement curve. You can also simulate with the normal model. And with the bias model, you can have from our website for LT-Spice, you get the blue curve. And also here you can see the resonant frequency is shifting in higher frequencies. That means, for example, if you have a noise on 100 megahertz and you simulate with the normal value, or have a look on the data sheet, you think, you had a lot of impedance on this point, but in the real world, it drops down, nearly down by 10, by factor 10. And this both effects are combined in the pi filter or in the LC filter. I will show you a little bit later. What possibilities you have for capacitors if you use, for example, a 100 nanofarad capacitor like this blue one here at, for example, 50 volts. You have a drop down to 40 nanofarad. That means this capacitor only have 40 nanofarad on your working point. And to try or to see what happens with your filter in a simulation, you can change to another capacitor with a start value at 0 volt with around 47 nanofarad. Then you get nearly the same result. Or the other way would be to use a model which can detect the DC bias voltage for capacitors. That's the other way to find a solution. And the same thing you can do with the ferrite. You have also the blue curve for a standard product without any current. And if you use it with current, then you need another one It's also shifted to a higher frequency. Then you can do the same, or the second method, you can also use a bias model, a special bias model for simulation to reach your goals. This is what you can see at our tool Red Expert on our website. The blue one is the standard one. You can also find in the data sheet at 0 amps, the component. And if you like to know what happens at 1 amp, then you can change in Red Expert by a drop down and select the 1 amp, and you can see the curve for 1 amp. And in principle, the same you can simulate in LT-SPICE. Now we come to the simulation. I do the first simulation on top here. I marked it with the black line. Then we can see in the next slide the black curve for this simulation part. This one is without any bias effects, without voltage bias and current bias for capacitor and inductor or ferrite. The second one will be the blue curve in the simulation. In this one, I use only the current bias of the ferrite here. I change this component to a biased version. And in the third, the red one, I use both voltage and current bias. I change, or I use the same model like here, and I change the capacitor to a bias model from us. And yeah, the result, the black one is the standard one with standard components, with standard parasitics. The blue one will happen if I use the pi filter with a current which is flowing through the design. And in reality, often happens that you have a lot of current. And if I have also the voltage which is driven the current, then you get the red curve. And yeah, it depends on the frequency you will filtering if you get trouble with the filter or not. That's the question. If you have a look on here on the 20 megahertz, for example, you expect a lot of attenuation, but maybe the red one is the realistic curve for voltage and current bias. You get less attenuation as you expect in your design. And maybe it's too less and you can't reach the specification you like. Yeah, that's the fact what I want to show you today. And yeah, now I think we have a look on your questions and I try to answer everything. Okay. Yeah. One question I see here is if you could download the presentation after webinar. Yes, we will give you the presentation in the download section. At the end of this webinar in the next days. The
Hi,
next question. Yeah.
Robert. Apologies about that. I was having some technical difficulties.
No problem. you
Excellent.
can. Yep.
All
You
right.
can.
Yeah.
Yep. You can start with the questions.
Okay. Excellent. Were you able to go over any during my absence?
Yeah, at the moment I have only answered the question about the download of the presentation.
Oh, okay. Excellent. Excellent. Yeah. And as you did mention, we will be sending that out within the next week or so, along with a video on demand. Thank you for that. We do have some questions rolling on in. Our other question here: where do you get the component models from?
You can have the models from our website. That's one way to download it. Also for the beads or the chip beads for the bias models are available on our website. Or some of the components are inserted into LT-SPICE directly. You can also use these models. And for the capacitors, we are not ready up to now with the bias models. But if you like, you can contact us directly and we can see what we can do.
And kind of rolling on into that question, do the models are they also available for P-SPICE instead of LT-SPICE?
Yes, we have it on the website for P-SPICE, but only the standard models, not the bias models at the moment. Let's take sometimes more, and but we will bring it on the website, yes, in the
Perfect.
future.
Slowly but surely. Our next question here: do the filter effects strongly depend on the component size?
Yeah, not so much. I think I show you some difference on yeah, the 08, 05 to 06, 03, but the difference in measurement is not so much, and also in from simulation side is not so much. Other parasitics are yeah, results in more or in much more difference of the attenuation curve.
All right, excellent. Next question here: does filling the holes of the via, maybe with solder, help in lowering the inductance value?
Yes, a little. That's also a possibility to handle thermal stuff. It goes in the same direction. Sometimes if you try to yeah, bring temperature from one side to the other, you can do a lot of so-called thermal wires or plugged wires. But you have a border yeah, um, for the count of wires, which is yeah, possible to bring down the impedance of the sum in parallel. If you have or it's not useful to do more than 3 normal wires or also plugged wires in parallel for getting a lower impedance because of yeah, the mutual inductance of the influence of the wires in between. And for this, it's only for thermal things to have more than 3 ones.
Mm-hmm. Okay, excellent. Our next question here, they are asking, did you try to simulate circuits without thermal relief for vias?
Um, Not real. No. That's yeah, we have the thermal relief for wires in the board. I think you saw it. But for simulation, we change nothing, or we don't try it. What happens? Or no,
Okay.
not at the moment.
Okay. Our next question here, we'll take a couple more and then we will wrap up today's webinar. Again, if you have any questions, ask them in the questions box, or if you think of them later, simply reply to our follow-up email from webinar team at we-online.com. Do your L and C models include the internal parasitics of the components themselves in addition to the PCB parasitics?
No. The models for the components are only the internal parasitics and nothing from the PCB side. From PCB side, yeah, there exists some calculations, some tools you can use for calculating copper track, for example, or the wire itself, but it's not a part of our components. You must simulate, especially I show you on one of the first slides, to put an extra inductance with a small value, but not in our component models.
Okay, excellent. And then this will be our last question for today's webinar. I do see more coming on in, but we will answer them in an email or with a phone call or a customer visit after today's webinar. Does the filtering get much worse or higher voltage where the ground plane has to increase distance from the top layer?
Yes, in principle, yes, because if you increase the distance from the top layer, you have a longer line in principle, more copper, and if the distance increase, then also the impedance will increase. If you have the same construction, if you have, for example, one wire, the inductance will increase if you increase the distance.
Okay, excellent. Thank you, Robert, for presenting and joining us for today's webinar. I appreciate it.
Yep, you're welcome.
And thank you, everyone, for joining us today. Again, if you have any more questions, simply reply to our follow-up email or just email us at webinarteam@we-online.com. I'm Amelia Thompson. You can follow me on LinkedIn. You can also follow our Würth Electronic page on LinkedIn to learn about all upcoming webinars. And don't forget to listen to the Würth Electronic What's Up radio podcast, where each week we are bringing our application notes, our blogs, our press releases, and so much more to an audio format. That is the What's Up podcast, and you can find that on all podcast streaming networks, including iTunes, Google Podcasts, Spotify, and so much more. And only 2 webinars remain for 2022. We will return in 2023, but join us for next week's webinar. One of the finals with Frank Puhani presenting DC link capacitor specifications and applications. Register online at www.we-online.com/webinars. I'm Amelia Thompson, and I hope to see you soon.